Welcome to The Explainer. We're all about taking really complex topics and breaking them down into stories that are super clear and easy to follow.
All right, welcome back, everyone. So this is part 3 of our big 11-part journey through the comprehensive report on generative AI and large language model comparisons from Virtualization Options LLC. Now, in our last explainer, we really got into the weeds of the transformer architecture, the magic behind all that text generation. But today, we're shifting gears completely. We're diving headfirst into Chapter 3, and this is where it gets really creative. We're talking about the engines that actually generate the visuals and the audio we see and hear.
So that brings up a really big question, right? How in the world does an AI learn to paint a picture or compose a song? Well, it turns out that making pixels and sound waves, that requires a totally different kind of blueprint than just making text. It's a whole different ballgame. So let's get into it.
Right, so our first stop, going beyond just words. We're going to look at why the AI that's great at writing a poem, well, it can't just turn around and paint a portrait. It needs a whole different set of tools, and we're about to find out what they are.
Okay, so while the world of text generation is pretty much dominated by those transformer-based LLMs we talked about last time, when you get into sound and visuals, it's a completely different universe. You need entirely different approaches. The key takeaway here is that we need specialized tools for these different creative jobs, right? Each one has to be optimized for its own unique challenge. I mean, you wouldn't use a hammer to paint a masterpiece, and in the world of AI, you definitely don't use a language model to compose a symphony.
Okay, let's talk about our first major blueprint. This one's a real game changer. It's called GANs, and it's basically like an AI art forger. We're about to see how a really clever competition between two AIs totally unlocked the door to creating images that look incredibly real.
So GANs, that stands for Generative Adversarial Networks. And the name really gives away the secret. This whole thing, which kicked off back in 2014, is basically a duel between two neural networks. You've got one called the generator and another called the discriminator. And they're locked in this adversarial process to create synthetic content. The core idea is just fascinating. It's an AI showdown.
Okay, so how does this duel actually work? Well, first you have the generator. It just starts by creating something from random noise, basically digital scribbles. Then the discriminator network steps in. Its job is to look at that creation and say, is this real or is this a fake? It's the detective. This goes back and forth until you reach what's called convergence. That's the moment the generator's content gets so good, so convincing, that the discriminator just can't tell the difference anymore. It's like an art forger and a critic locked in a room. The forger just keeps painting and painting until the critic is completely fooled. That's the win state.
So yeah, you've got these two competitors. The generator is the creator, the artist. Its whole job is to get better and better at making realistic stuff based on the feedback it gets. And then you have the discriminator, the critic. Its only job is to be a really tough judge, to spot the fakes, and push the generator to improve. It's this constant battle, this push and pull, that drives the whole system forward and gives us those absolutely incredible photorealistic results.
But GANs aren't the only game in town. There's another, more recent approach that's really taken over, especially for creating super detailed images. We're talking about a technique called diffusion, and it's like sculpting from noise.
So what are diffusion models? Well, the idea is totally different from GANs. These models work by taking a perfectly clear image and then, step by step, they add random noise to it until it's just a mess of static, completely unrecognizable. Then, and this is the genius part, it learns how to perfectly reverse that process. Instead of a competition, it's more like a restoration artist who learns how a masterpiece falls apart just so it can learn how to put it back together perfectly.
So, the process starts with pure random noise. Literally, think of a screen of old-school TV static, just a complete jumble of pixels with no rhyme or reason.
And then, the magic happens. The model meticulously reverses the chaos. Step by step, it starts to clean up that noise, guided by your text prompt, until a masterpiece emerges. It's not a sudden creation. It's a careful, iterative process of refinement. It's literally like a sculptor chipping away at a block of marble to reveal the statue inside. So let's put these two side by side. You've got GANs, which are all about that adversarial competition. Their big strength? They can be super fast and achieve some seriously photorealistic results. But that constant fighting can also make them a bit unstable, kind of hard to train. Then you have diffusion models. They're all about that iterative refinement, reversing the noise. They're like meticulous sculptors. They take their time, and they're often slower and need more computing power. But the payoff is incredible detail and way more control.
That's why they're behind the big names you've probably heard of, like Stable Diffusion and DALL-E 3. Okay, so we've talked about static images, but what about the sound of AI? What about creating stuff that flows over time, like a piece of music or someone talking? Well, that requires a whole other set of blueprints, because now you're not just dealing with pixels, you're dealing with time and sequence. And that changes everything.
So for sound, there are a couple of main blueprints. First up, you've got something called variational autoencoders, or VAEs. Think of these as learning the essence of a sound. They learn to compress audio down into its core components and then rebuild it. It's how an AI knows what a trumpet sounds like. Then you've got autoregressive models. These are all about sequence. They generate audio one tiny little piece at a time, predicting each new sound based on everything that came before it. This is what gives music its flow and coherence. So you can kind of think of it like this. The VAE learns the quality of the instrument, and the autoregressive model learns how to play it in a way that makes sense.
Okay, this is where it gets really exciting. We've talked about separate blueprints for images and sound, but what happens when they all start to come together? Let's look at the future, a unified canvas.
And the ultimate challenge? Generating video. I mean, think about it. It's not just about making one good frame. You have to ensure smooth motion, right? Objects have to stay consistent from one frame to the next. They can't just disappear and reappear. You have to model really complex scene dynamics. And on top of all that, every single frame has to be visually coherent. It's the ultimate test, combining the difficulty of creating an image with the added dimension of time. This is the massive puzzle that models like Runway Gen 2 are trying to solve right now.
And this really is the cutting edge of the field. We're moving towards what's called multimodal integration. That's a fancy way of saying we're building single models that can handle text, images, and sound, all at the same time. No more separate tools. This is where you get those mind-blowing new capabilities, like typing in a sentence and getting a full music video back. It's a huge leap forward.
I mean, as these technologies keep getting better, the lines between different types of content are just dissolving. It's opening up completely new ways for us to be creative. These integrated systems, they promise tools that feel more natural, that feel more like how we actually think, right? When you have an idea, you don't think of it as just words or just a picture. It's all mixed together. And that's the future these models are racing towards.
And all of this leads to a pretty deep question, doesn't it? As these tools merge and become more powerful, are we just building a better paintbrush? Or are we building a creative co-pilot? What does it mean when our tools don't just follow a command, but actually seem to participate in the creative process with us? That's a huge thought to chew on, and we'll definitely be exploring it more as we continue this series.